Hello everyone, my name is Ashutosh Rai and I'm going to talk about a problem called set restricted disjoint paths. So let me share my screen so that okay. So this is the title of our work, Parameterized Complexity of Set Restricted Disjoint Paths on Chordal Graphs. And this is a joint work with Petr, Golovach, Fahad, Panolan, Saket, Saurabh and myself. And first I'll give an outline of the talk. So first I'll introduce the problem, disjoint paths and set restricted disjoint paths. Then I'll give a brief overview of the area of parameterized complexity and kernelization. Then I'll talk about the previous work that has been done on this problem in the parameterized complexity area. Then I'll go slightly deeper into the results and briefly talk about the techniques that we use to arrive at the results. And then I'll conclude with the open problem. So first, let's talk about the disjoint paths problem. So in the disjoint paths problem, we are given a graph G and we are given a set of k terminal pairs S1, T1 to SKTK. And we are asked whether there exist k vertex disjoint paths between the terminal pairs. So what we want to do is find like k paths P1 to Pk such that P1 is a path between S1 and T1, P2 is a path between S2 and T2, Pk is a path between Sk and Tk, such that P1 to Pk are vertex disjoint. And this problem is known to be NP-complete even on interval graphs. So of course on general graphs it is NP-complete, but even on the restricted graph class of interval graphs, it is known to be NP-complete. In this work, we also consider, actually, this is the problem that we consider, which is a generalization of disjoint paths, which is called set restricted disjoint paths. In this, in addition to the graph G and the terminal pairs, so we are given a graph G and terminal pairs S1, T1 to SKTK. And we are also given some domains, K domains basically, from where the vertices of the individual paths can come from. So what we want to find k vertex disjoint paths, P1 to Pk. So P1 is a path between S1, T1, P2 is a path between S2, T2, and Pk is a path between Sk, Tk, such that they are vertex disjoint and the vertex set of each of the paths come from the respective domains. So P1, vertex set of P1 is a subset of U1 and so on. Vertex set of Pk is a subset of Uk. So this is clearly a generalization of the disjoint paths problem because we can keep all these domains to be the vertex set of G, which is V. And then this is exactly the disjoint paths problem. So of course, since this is a generalization, this is also NP-complete on interval graphs and also on chordal graphs because chordal graphs are a superset of interval graphs. Now let's talk about parameterized complexity and kernelization. So these problems are NP-complete and parameterized complexity is one paradigm to deal with NP-completeness. So here, in addition to the input, the problems also comes with a parameter K. Okay, and we want to design an algorithm with running time f of K polynomial in N, where the f is a function of K alone. So f does not depend on N. And the problems that have such an algorithm are called fixed parameter tractable or FPT. So why such a running time? One may ask. So we cannot expect this f to be polynomial because then we'll have a polynomial time solution for an NP-complete problem. So this f is essentially going to be exponential, but we want that the exponential part is independent of n. So the dependency of the running time on n, we want it to be polynomial, and we want the exponential blow up to be confined in k, right? So that if the parameter k is small, then we still have an efficient algorithm, right? So if k is some constant, then we get a polynomial running time, for example. Another related field to the field of parameterized complexity is the field of kernelization. And what is a kernelization algorithm? Kernelization algorithm does not solve a problem completely, but given an instance. So an instance of a parameterized problem looks like x comma k, which is a subset of sigma star cross n, where this sigma star denotes the input and this natural number is the parameter k. So x is the input and x comma k we want to figure out whether it belongs to a given language or not. So it is an instance of L. So given an instance of L, what does the kernelization algorithm do? It takes polynomial time in the input size and outputs another instance of the same problem. So it outputs x prime comma k prime, a parameterized instance of an instance of the same parameterized problem, such that the new instance is a yes instance if and only if the original instance was a yes instance. So there is equivalence between the new instance and the old instance. And the size of the new instance is bounded by a function of k alone. Okay, so size of x prime and the new parameter k prime both are bounded by a function of k, where k is the original parameter. So observe that here the size does not depend on the size of x. That means the size of the output instance of a kernelization algorithm does not depend on the input size. It is bounded by a function of the parameter alone. And that's the main thing that we want from the kernelization algorithm. As I said, the function p has to be polynomial. The time taken by the kernelization algorithm has to be polynomial. And f here can be any computable function. And when f is polynomial, when the size is bounded by a polynomial function, then we say that the problem admits a polynomial kernel. And it is a folklore result in the field of parameterized complexity that a problem admits a kernelization algorithm if and only if it is FPT. So it can be asked that why study these two things differently if they are one and the same. So the kernels that we get from this theorem actually give exponential are actually exponential. So if a problem turns out to be FPT and from there we derive that, okay, it has a kernel, that kernel is exponential. So then the question becomes that does this problem have a polynomial kernel? Which means that can in polynomial time, we can, given an instance of this problem, can we reduce it such that the size of the output instance is bounded by a polynomial function of the parameter, which is not something that we directly get by this folklore theorem. But this nevertheless implies the relationship between kernelization and FPT. So now some previous work on these problems in the field of parameterized complexity. So disjoint paths is a very well studied problem in the field of parameterized complexity. And the first algorithm was given by Robertson and Seymour in their GraphMiner project, which gave an algorithm with running time f of k n q. And it uses the irrelevant vertex technique, which became quite an important algorithmic tool later. But the thing was that this f in their f of k n q was a very fast growing function. So effort started to look at restricted graph classes and bringing this f down. And one of those graph classes where this was studied was planar graphs. So Adler et al. Proved that this problem, disjoint paths, can be solved in time 2 to the order k n square on planar graphs. So in double exponential time on planar graphs, this problem could be solved in a parameterized sense. And recently, Lovstanov et al. Designed an algorithm which ran in single exponential time for planar graphs. So this was a breakthrough result, and it showed that on planar graphs, disjoint paths can be solved in 2 to the big O of k square time, and some polynomial factors in n. Another restricted graph class on which disjoint path has been looked on is Chordal graphs. So Kammer and Tholi showed that this problem is FPT on Chordal graphs. In particular, they showed that this can be solved in time 2 to the big O of k log k n plus m. And their technique actually reduces the tree width to find this FPT algorithm. Now, the other more general problem, set restricted disjoint paths that I talked about. So it was introduced by Belmonte et al. And there they showed that this problem is strictly harder in the parameterized setting because on general graphs, this is hard for k equal to 2. That means if we are given just two terminal pairs, then SRDP cannot be solved in polynomial time. And this is in contrast to disjoint paths, which is FPT. Hence, for k is equal to 2 or for any constant k actually, it has a polynomial time algorithm for general graphs using the results of Robertson and Semler. For Chordal graphs, they showed that this problem is in XP, which is a class which basically has this kind of running time n to the f of k. So this is not exactly FPT time. For fixed k, it still gives polynomial time algorithm, but the degree of the polynomial grows when measured in terms of the input size. So what we want to actually separate this f of k and have a constant power here with n. And An et al. Studied this set restricted disjoint paths problem on well-partitioned chordal graph, which is actually a subclass of chordal graphs, and it generalizes split graphs. And they showed that this problem is FPT on well-partitioned chordal graphs. So it is FPT on well-partitioned chordal graphs. It is not known to. It was not known to be FPT on chordal graphs. For chordal graphs, the best thing that was known was XP, and the kernelization status of this problem on chordal graphs is also not known. So we wanted to explore this, and also I just want to mention that kernelization question of disjoint paths on chordal graphs is also not known. So for this generalized problem for set restricted disjoint paths, we show that this problem is FPT on chordal graphs, and we also show that it does not admit a polynomial kernel even on interval graphs, which would imply that it does not admit a polynomial kernel on chordal graphs as well. So for chordal graphs, we settle the parameterized complexity of SRDP, and that is the main contribution of this work. So how do we approach the problem? How do we show that this problem is FPT on chordal graphs? So let's look at the structure of chordal graphs first. So what are chordal graphs? Chordal graphs are the graphs which do not have induced cycles of length 4 or more. They are also called triangulated graphs. And these graphs have at most n maximal clicks, where n is the number of vertices in the graph. And these maximal clicks can be arranged into a click tree. And what is this click tree? In this click tree, the vertices of this click tree, so this click tree is a graph, you can assume it to be a graph, where the vertices of this graph are the maximal clicks of the chordal graph G, and two bags or two vertices of this click tree share an edge if they have a common vertex. So a vertex might belong to many maximal clicks in the chordal graph, and maximal clicks are the vertex set of this graph, and the two vertices share an edge if they have a common vertex of the original graph. So since this terminology of vertices can get confusing, we call them bags. So we call the vertices of the click tree bags and the vertices of the original graph vertices. So we represent a click tree by f comma beta, where f is a tree and beta is a function from the vertices of this tree to the set of subsets of the graph of vertices of the graph G. Okay. So this click tree actually also gives a valid tree decomposition for a chordal graph, and this is the property that we'll be utilizing for doing some dynamic programming on graphs of bounded tree width on our chordal graph. So what is our idea? Idea is to bound the tree width of the graph by reducing the click size, because the maximum click size is the maximum bag size in the tree decomposition. And if we reduce the click size, then the tree width also gets bounded. And then we do a dynamic programming on bounded tree width graphs. So that is the main idea for showing FPT. So if we can reduce the click size as a function of K alone, then it might work, right? So for that, for reducing the click size, what do we do? So first we look at terminal pairs which share an edge, which already have an edge between them. Then we don't really need to do much to connect these terminal pairs, so we just remove them. Right? So we remove those terminal pairs which already have an edge between them and basically just remove that requirement. Now for every pair SITI, there is no bag where they occur together because there is no edge between them. So there is no maximal click of the graph G which contains both of them. So the bags in which SI and TI occur are disjoint. So we find a unique path of minimum length, basically, between the click tree, between the bags which contain vertices of SI and the bags which contain vertices of TI. So there are some bags which contain SI, there are some bags which contain TI. We look at the shortest path between these sets of bags. And this is going to be a unique path because these sets are going to be connected in the tree because of the connectivity property of the tree decomposition. So now what do we do with this click path, right? So this click path is going to have some end vertices where SI and TI occur. And none of the edges, none of the bags in between SI and TI occur because then we could shorten the length of the path. So now, except these two bags, the endpoints of this unique click path, we delete SI and TI from every bag. And why we can do that? Because any path of shortest length, any induced path basically between SI and TI will not use any of the vertices which are not in these bags. So this is one reduction rule. And another reduction rule is we delete simplicial vertices. So what are simplicial vertices in a graph? Simplicial vertices are the vertices whose neighborhood is a click. So why can we delete simplicial vertices? Because if a solution uses simplicial vertex, I can find another solution which does not use it by just going between its neighbors. Because its neighbors are already being used, so we can short circuit this path. So we can delete simplicial vertices from the graph. And what this rule means is that every leaf bag will end up having a terminal, because if it does not have a terminal, then since it is a maximal click, it will have a vertex which is only part of this bag, and that vertex will turn out to be simplicial. And then rule 3 must have deleted it. So that's why every leaf bag must have a terminal, and this bounds the number of leaf bags by at most 2k. And by the property of a tree that the number of degree at least 3 bags is at most the number of leaves, we also bound the number of at least 3 bags. That is also bounded by 2k. So what do we do with these bounds? So now we look at any vertex, any bag of degree at least 3 in the click tree, in the tree decomposition. And now we look at any SITI such that this bag of degree at least 3 occurs in the path between the SI and TI. And now we mark some vertices in this bag. So we use the click path, and this vertex is occurring in between. This bag is occurring in between SI and TI. So we mark 2k plus 1 vertices which go towards SI, which go the farthest towards SI, and we mark 2k plus 1 vertices which go farthest towards TI. And we mark vertices only from the domain from which the vertices are allowed for a path in SI and TI, right? So what do we want to achieve by this marking? After this, we delete the vertices which are not unmarked by, remain unmarked after this procedure. And the idea is that the marked vertices in the bags are better suited to connect SI and TI. So we mark 2k plus 1 vertices which go towards TI, which go farthest. So any vertex that gets deleted from this bag, there are at least 2k plus 1 vertices which are doing the job better than this vertex, which can have better connectivity, which can go farther. And at most some 2k or 2k minus 2 actually of them can be used by other paths between other SI and TI. So we are still left with at least two vertices which can do our job, and hence marking this 2k plus 1 vertices on either side suffices, and we can delete the unmarked vertices. And after this, the size of any bag in which has degree at least 3 is bounded by order KQ. And this basically leads us to the only problem of bounding the size of degree 2 bags. Actually, we can do the same procedure with degree 1 bags also, and that bounds the size of degree 1 bags. So the only thing that we are left with is bounding the size of degree 2 bags. Then we'll be able to bound the tree width because we would have bound the maximum click size in the graph. Now we consider click paths such that the endpoints are not degree 2 bags, but every internal node has degree 2. So the endpoints are degree 3, or they have terminals and such that their size has already been bounded, or they are leaf vertices. But all the internal nodes have degree 2. And now we want to bound the sizes of such bags, all the internal nodes. And for each internal node, again, we do a marking procedure. And in that, we first define an ordering of the vertices. And we define this ordering only for the vertices which do not occur in the degree greater than or equal to 3 nodes, because they are already bounded. So they are going to contribute at most k cube to the size of this degree 2 bag. So we don't mark them. We mark only the vertices which occur on this path. The vertices which occur on the endpoints, we don't mark them. And again, we mark some 2k vertices which are highest in this ordering. And this ordering also is kind of, which vertices go the farthest and so on, but it is slightly more complicated because of technical reasons, but in spirit, it remains the same. And again, because of some technical reasons, we have to consider the nodes in order. So either from right to left or left to right, we have to traverse this path of degree 2 nodes or bags. And in that order, we need to mark these vertices. We need to mark some more vertices to preserve connectivity property of the tree decomposition, because after this, we want the marked vertices to remain in the graph, and we want them to satisfy the connectivity property of the tree decomposition. So we need to mark some additional vertices also in addition to these 2k plus 1 vertices. But after doing all this, if we delete the unmarked vertices from a bag, we have that the size of degree 2 bags is bounded by k cube, and this finally bounds the tree width of the graph by order k cube. And now, since we have bounded the tree width of the graph, we want to give a dynamic programming algorithm. So this DP is not disjoint paths. So we describe a simple dynamic programming algorithm that solves this problem in tree width to the order k time on Chordal graphs with tree width TW. And this takes advantage of the fact that every bag in a tree decomposition of Chordal graph is a click. So this is the running time, tree width to the order k, and we have bounded the tree width by order k cube, right? So finally, we get the running time that SRDP can be solved in time 2 to the power order k log k on Chordal graphs, which shows that this problem SRDP is a FPT on Chordal graphs. We also show that this problem does not have any polynomial kernel on Chordal graphs. In fact, we show that it does not have any polynomial kernel on interval graphs. And for that, we use the cross composition technique defined by Bodlander et al. So in their work, they use the or cross composition more, but here we do an and cross composition. I'm not going to go too much into detail of this technique, but this is a very well-known technique for showing lower bounds, kernelization lower bounds. And it has very nice connections with the classical complexity. So here we start with many instances of an NP-complete problem and try to make one instance of the problem for which we are trying to show the lower bound, the kernel lower bound. So here we start with the disjoint paths problem on interval graphs, which is known to be NP-complete. And we take many instances of that. And we make one instance of SRDP such that the new instance of SRDP is yes instance if and only if all the input instances of disjoint paths were yes instances. And here we use the domain property of set restricted disjoint paths very crucially. So we restrict the domains of the path in such a way such that these paths, the one long path that we get in the new instance of set restricted disjoint paths, that implies that all the input instances of disjoint paths were yes instances. So here we use the domain property crucially, and that is why we could not make it work with disjoint paths on chordal graphs. We could not show the lower bound for disjoint paths on chordal graphs. And since we start with an NP-complete problem, which is disjoint paths on interval graphs, this shows that SRDP cannot admit a polynomial kernel on interval graphs unless the pH collapses. So it is known that if we start with an NP-complete problem and we get to an instance of our problem, then the problem does not have a polynomial kernel unless polynomial hierarchy collapses. So this is the final theorem that we show, that SRDP does not admit a polynomial kernel on interval graphs unless NP is a subset of co-NP/poly. So this is the more technical thing that is proved, and this implies that the pH collapses. It is already known that this implies collapse of pH. So this way we show that SRDP does not admit polynomial kernel on chordal graphs as well, because chordal graphs is a superclass of interval graphs. So we settled the parameterized complexity of SRDP on chordal graphs. But yeah, so this has been our more main contribution, that we showed that this is FPT on chordal graphs and it does not admit polynomial kernel on chordal graphs. In fact, even on interval graphs, it does not admit a polynomial kernel. But we were not able to solve what we feel is a more important question, which is if we can find a polynomial kernel for disjoint paths on chordal graphs. And this SRDP negative result, as I said, does not seem to work with disjoint paths because it utilizes the domains property quite crucially. So this is an open question for those who want to work on, and thank you for your attention.